This is the second in a series of videos in which I'm presenting ferroresonant transformers, and this is an example of a ferroresonant transformer. On the face of it, it looks very typical of a standard transformer, but they actually operate in a very different way. In the first video in this series, I demonstrated the advantages of using this type of transformer in that they have very good self-regulation. Probably an order of magnitude better at least than a standard type of transformer. And I demonstrated that over a very wide range of input voltages and output loads, they give very predictable and stable output voltage. Over the years, I've designed hundreds of standard types of transformers, but I've only ever designed a small handful of ferroresonant transformer systems, and that is because their applications are fairly niche. And you'll see why that is, hopefully, as I go through the explanation as to how this type of transformer works. Now, there are many designs for ferroresonant transformers, and there are different ways in which they can be wound. There are different ways in which the detail of their design can vary. But this is a fairly typical one, which is why I wanted to use this for these videos. And as we go through this video, I'll explain the basics of how this works. By necessity, I'll try and keep the explanation as simple as I can, so I will be abridging some of the explanation, but I'll try and keep it as concise and accurate as I can. I won't go into the mathematics of this, it does get quite involved, but I think the easiest way to explain how these work is to first explain how a standard transformer works, and then we'll look at how the ferroresonant transformer types vary from that. Now, firstly, with this transformer, the only parts that are really part of the ferroresonance system are the transformer itself and this big capacitor at the front. This capacitor, the rectifier and the connector block are not really part of the ferroresonant transformer system. So before I start the explanation, we'll just have a quick look at the way that the transformer is assembled. So what we have here is what looks like a standard transformer core, and it's the same material, it's laminations, and even the general form of it in terms of if it's a T or T and C pieces or E and I pieces can be the same. But where they really differ is that you see the windings are separated by this section here, and this section in the middle is a magnetic shunt. And I'll explain why that's there later on in this video. But the important thing to bear in mind here is that this shunt is a very important part of the operation of this type of transformer. So in this particular transformer, this top section is actually the primary winding. So that's what we apply the mains input to. And at the bottom we have the secondary windings. And the secondary windings on this particular transformer are in three parts. We have the basic output part of the transformer, that's our main secondary voltage output. That's the one that we were deriving the voltage from that we looked at in the previous video. There's then another winding in this section that is only connected to this resonant capacitor. And then in this particular transformer there's a third winding for other purposes, but that's not necessary and it's not part of the ferroresonance system. Okay, so that's the way it's structured. There's nothing else in here. It is just laminations making a standard core, a couple of windings and the magnetic shunt. One thing you can't see is there is air gaps down between each side of the magnetic shunt, and they're quite important to the operation in terms of setting its performance and operating point. And again, I'll come back to that later on, but just bear in mind that the general structure is laminations, shunt and the windings themselves. So I'll just get this out of the way. To best explain how a ferroresonant transformer works, it will be easier if we first start by recapping on how a standard transformer works. So if you imagine this is the core of a standard toroidal transformer, then the transformer is made up from the core and at least two windings. So we have the primary winding, and then we have the secondary winding. Okay, so exactly how these are arranged on the core is not particularly important. They might be on top of each other, they might be at opposite ends of the core. It doesn't really matter. As long as they're wound around the common core, then the transformer will work. Now, the way this works is fairly straightforward, but what you have to remember is that as I'm going through this description, this is an AC machine. So what I'm talking about voltages and currents, is a varying voltage and current that's been applied to the transformer. So we'll normally be applying a sine wave to the transformer windings. So this bottom winding is the primary, and at the top we have the secondary. And what's going to happen here is, as the voltage in one half phase of the mains starts to increase, it's going to induce a flux into the core of the transformer. So the flux is just really the magnetic energy being stored within the core of the transformer, and that flux will of course go right around the transformer. Its magnitude will depend on the current flowing through the primary winding, or at least initially on the current flowing through the primary winding. So as the voltage increases and the current increases through the primary winding, so the flux will increase as well. Now if we ignore the secondary for now, if we just keep increasing the current through the primary winding, then at some point the core will run into what we call saturation. That is, the core flux cannot increase any further. It's gone as far as it can, it's stored as much energy as it can, and all that's going to happen if you go beyond that is you're going to start heating up the primary winding. It then just becomes a resistor, and the core of the transformer cannot store any more energy. So if we look at that in terms of a graph, then we have the voltage increasing and the flux increasing. So if we say the X scale is the voltage and the Y scale is the flux, they will start off in a fairly linear fashion. So as the voltage increases, the flux will increase, but beyond a certain point we'll reach what's called the knee, and the flux increase will drastically level out. So even though you'll carry on increasing the voltage, the flux cannot go any higher. And normally in a standard transformer you must avoid going into this region of the curve, otherwise the transformer will overheat and probably burn out. The way the transformer works is that as long as the primary is not being driven into saturation, that is, as long as you've got enough turns and the current's kept low enough in the primary, then we'll get the flux alternating every half cycle. So first it will go in one way, then it will reverse and go the other way for the next half cycle, and the energy is recovered. So as the current in the primary reverses, the reason that the energy is recovered into the main system is because the energy was stored in the core and it's recovered in the next half cycle, and then that so just keeps repeating. However, if we put a load on the secondary, so if we attach a load across the secondary winding, then of course we also get a current flowing in the secondary winding, and because this then is, if you like, the same as the primary, so we have a current flowing in the primary that is coming from the main supply, but we're also now getting a current in the secondary. The only difference is this current creates a flux that opposes the flux generated by the primary. So it will generate a flux in the core, but in the opposite direction to the flux generated by the primary winding. And the result is it will reduce the flux generated by the primary winding. That will cause the current in the primary winding to increase to push the flux back up to where it was. And that's how the energy transfer between the two windings takes place, that as the load on the secondary increases, the reversal of the flux that's being generated by the secondary winding causes the current in the primary to increase to keep the flux generated by the primary up to the level that the transformer wants to try and generate. That's why the load, or the current drawn by a transformer, is low when there's no load, and why the transformer is able to respond and transfer more energy through the core as you apply a load. That principle of the secondary generating a flux in the core is very important to the way that a ferroresonant transformer works, so just bear this in mind as we start to look at the ferroresonant transformer. The main difference with the ferroresonant transformer is that while the primary always stays, or should always stay, within this linear region, the secondary is designed to always run in this flatter saturated region. And that obviously begs the question, how can we have one winding on a common core in a linear part of the flux curve and the other winding in a saturated part? And that comes down to the way that the transformer is physically structured. So I'll get rid of this and we'll look at the general core design for a ferroresonant transformer. So if we look at the basic core structure, it looks like a standard transformer structure. So these are the laminations, and quite how they're split will vary depending on the design. It might be an E and I sections, or it might be a T and C sections. It kind of depends on the particular design. But the result is the same. You start off with a core with this form. And this, if you've ever seen a standard transformer, is exactly the same as a standard transformer. Where it varies is there is an addition to ferroresonant transformers that are a key to the way that they function. That is, they have magnetic shunts, which is what these are. And these are the shunts I showed on the core that sit between the two windings. So what we have is a winding at the top, in this case, and that is the primary. And then we have a winding at the bottom, and that's the secondary. And then there's another winding, and that's our resonant winding. The resonant winding connects to nothing else but the capacitor. The secondary winding is the winding we connect to our load. In this case, the example I showed, it was a rectifier and capacitor. And then the primary, of course, is connected to the main supply. And that's all a ferroresonant transformer is. The main difference between this and a standard transformer is the inclusion of the magnetic shunts. Now, the way that this transformer works is quite ingenious, but it's also quite simple as long as you understand the principle of the standard transformer. So I'll try and keep this as simple as I can, so I'll be skipping over some of the detail just to try and make this clear. But the way that this will function is when you apply a current to the primary winding, then it generates a flux in the core, and that generates a voltage in the secondary winding, but it also generates a voltage in the resonant winding. And because there's a capacitor connected across that winding, then a current is generated in this winding that is in phase with the primary current. There is also a voltage current, if there's a load attached, generated in the standard secondary winding. And because we have this capacitive winding in addition to the standard winding, and there's a capacitive load across it, this causes the same increase in the primary flux that we get in a standard transformer. It also creates an increase in the secondary flux. So in other words, this current flowing through here not only increases the current flowing through the primary as it does in a standard transformer, it does the same thing with this section of the transformer as well. So the reason that we want this winding to be here is it's to drive this part of the core into saturation. So in other words, what we're trying to do is increase the current and the flux in this part of the transformer that these two windings sit on, such that it drives it into the non-linear portion of the flux curve. So in other words, we want it to operate in this part of the curve. But in order to stop this saturation also affecting this part of the core, we have these shunts. And what these are here for is they cause the flux path to take a shortcut. So instead of it going right round, if these weren't here, then the entire core would become saturated. But because these shunts are here, they form, if you like, a shortcut for the flux, and it then will prevent a proportion of the flux getting back to the primary part of the core. And the same thing with these section is the shunt will have the same effect, and it will tend to separate the primary flux field from the secondary flux. Now, you can't separate them entirely, of course, because they do need to be coupled together, and that's why you have these air gaps. And the size of the air gaps, the size of the shunt, and the design of the core are such that the amount of coupling between the secondary turns, secondary windings, and the primary winding, and the resultant interaction between the two parts of the transformer are designed to make sure that the transformer can operate under its nominal load configuration or design, such that the secondary is operating in the flat saturated section and the primary is in the linear section. So the next question is, why do we want the secondary to operate in the saturated region of the flux curve? So if I redraw the flux curve, we have the knee here, and bear in mind the primary is always operating in this linear zone. We don't want the primary to be driven up into the saturated zone, which is why we have the shunts in the core. But the secondary, because of the capacitive current that's flowing in the secondary resonant winding, is driven into saturation, and as I say, it's isolated from the primary flux by the shunts. And because the secondary is operating in this part of the curve, let's assume that at any instant it is here. If for any reason the load on the secondary changes in such a way that the flux within that part of the transformer moves this way, then you can see it's not going to have much of an impact on the voltage. The voltage range over this part of the curve is very small. So whichever way it moves, then the change in voltage is going to be very small. So this is kind of the principle on which it operates, that where because the secondary is in a flat portion of the saturation curve, it generates or creates a situation where the transformer is effectively operating in a range where changes in load or changes in input voltage don't really affect the output to any large degree. And as long as the transformer is properly designed, then we can have a 10-to-1 isolation ratio where the change in output voltage can be only 10% or less of the change in input voltage. So the next thing to consider with a ferroresonant transformer is the load design, and it is fairly critical to get the load design correct. If you just start to apply low voltage to the transformer, so low AC voltage, you'll find it will have a very high AC current. The current will suddenly start to drop once we get up into the proper operational band for the transformer. And if we draw that in terms of load and efficiency, then what we end up with is a curve where the efficiency, so if we say this is efficiency as a percentage, and if we say that's 100% and 0%, and then load again 0% to 100% load, then we end up with a bit of an odd looking curve that it looks something like this. So in other words, anything below, typically with this sort of transformer, it's anything below about 70% full load, this is load, will give you very poor efficiency. So these transformers can be anything upwards of 90% efficient at full load, but at 50% load they might only be 40% efficient, and that's because they do need to operate in a very limited range. That's why you can't really use them in linear supplies and that sort of thing, because I'm talking about here bench supplies, because otherwise when you run them at low output loads, then they'd be extremely inefficient and you'd get very poor performance. One of the other aspects of this, now I will do one more video on these transformers and show some more aspects of their operation. One of the other aspects of the way these work is if you short circuit the output of a transformer of this size, if it's a standard type of transformer, then you'll probably blow the fuse or do something very bad, and almost certainly the magic smoke will escape. With ferroresonant transformers they don't do that. If you short circuit the secondary, then it effectively shuts the transformer down and the power flowing through it drops off to a very low value. So it's an inherent safety feature of them. They're very good and have some very good strong points. Unfortunately, that also means that if you have a highly capacitive load on the secondary, then quite often they won't start up properly, because each time they try and start up, that high inrush current causes them to shut down. And that means that if you want to have a transformer driving a high inrush current system, then you have to make it a bigger transformer. The problem by making it a bigger transformer is that you then set its operation point higher up, which means that in normal operation, if there's a high inrush current but a low running current, then it will be very inefficient. So it's a balancing act with ferroresonant transformers to get their rating correct, to make sure that your shunts are properly designed to give you the correct coupling between the two parts of the transformer, and also to make sure that the transformer is capable of starting up properly in the environment in which you're trying to run it. Otherwise you'll find that it'll just keep cycling and clicking and it won't do anything, a bit like a faulty switch mode supply. But when you get them properly tuned and properly designed for a particular application, then they are extremely good, and that's why IBM use them so much in their computer systems, because the load was fairly consistent, the inrush current wasn't too high, and the self-regulation it gave them as the mains voltage varied was extremely good, and it gave them a very good stable operation for their systems. But as I say, they're not suitable for general applications because of the need to properly set their operating point to a given application. Okay, that's it for this video. As I said, I am vastly oversimplifying the operation of ferroresonant transformers. If you do want me to go into more technical detail, then please leave a comment. In the next video I'll give some more demonstrations of this transformer actually operating, show its short circuit protection feature, and also look at some more of the characteristics of it in terms of its startup and the currents that we can see flowing through it. So I'll use the current clamp and the scope, and we can have a look at the currents and see how they relate to the operation that I've been describing here. But hopefully you found that interesting. Comments welcome.